Hey Zoltan, I just want to check my microphone. Can you hear me well?
I can hear you. And can you also share your screen?
Sure, will do.
Hey, Helia, hello.
Hi.
Everybody's in. Jan is here, everybody's here. Good. Let me make an announcement on the Slack channel, people to join. Hi, Kuldeep.
Hey, hello all. Hello, Zoltan. Hello, Elia.
Looks like you all made it on the right time for now, so it's good.
Yes. Yeah.
Okay, your screen's working, June. Great. 1 second. Let me go back to the Slack channel. 1 second.
Just to confirm, like, do we also have a YouTube stream now or just? Okay.
Yeah, we should be live on YouTube now. I see a live sign. And also, those of you who have not received or who don't have the Slack channel for the BuildSys conference, send me a message and I'll do it slowly and invite you to it
Just to confirm,
for
like,
further discussions.
yep.
Healy, I saw your message and you're in the Slack channel, so I'm not sure, you may have to just zoom into it again, but I can send you a message over it.
So it's the previous Slack channel? Last year?
No, it's a new one, but I see that you're logged into it, so I can send you a message through it. I'll invite you again while you're talking.
Okay. Thank you.
Okay, let's give it a couple more minutes. I was trying to get the organizers to let us use the Zoom for everyone instead only for the authors, so we can have a better conversation. So hopefully people will try to join slowly over the, and send you a message through it.
So I just checked our YouTube stream and there are 2 people watching it. So maybe
Right.
those people are, no, now 3. Maybe it's me.
And from what I heard, it's also delayed by about 20 seconds.
Yeah.
So if you get a little bit of a delay on that. Okay. Okay, maybe one more minute. I think we're getting slowly converging to steady state. And with one more minute, then we get started.
Do you know if we are mostly virtual or there are people attending the workshop in person too?
Actually, good point. There are people attending in person. Some people are there for SenSys also. And if you're listening, take a picture, post it in the Slack channel, so we can see you. I think initially I didn't ask for a special room, but I think the organizers put in the room for everyone who is attending the workshops virtually. I mean, but then they're on site for the rest of the conference.
I am attending from the physical location.
That's Fred. Yes. Do you have a special room, or is it like everybody?
What they did is they gave two rooms, one for presenters, physical presenters, and one for attendees. But if you are, since there is only one room for all the workshops, physical attendees still have to wear headphones, but they are sort of physically in one space.
Cool. Awesome. Okay. Thank you, Fred. All right. So I think it's time. It's my pleasure to welcome you all for the second RLAM workshop. My name is Sultan Nagy. I'm organizing chair and for this workshop and the second edition, and last year for the first edition. As we started talking, there is an official Slack channel for the BuildSys conference. If you have the old one, the one that we as a group use throughout the year, you can stay on there too. Just tag me if you have questions, and I'll see it and I can relay it. So don't worry about it too much. Just because otherwise it gets too complicated. But I'll try to invite everybody throughout the day, and then we also have this channel going on. The organizers, they put out the live stream on YouTube, and they want the discussions on remote people to happen over Slack. We asked them to include everybody here because I remember this from last year. It was really good conversations that we could have, much better than just slacking. So hopefully it can be repeated to some extent. So that's for welcoming. June, if you go to the next slide, I just wanted to give a big thank you to the people actually did the work behind the scene. June from UT Arlington, Jan from Pacific Northwest National Labs, and Matthias from National University of Singapore, who put together a program. They put together the website, put together all the information, and make me look good to show up and say hello. And so I think that's a great program that we're looking forward to, and we're moving to getting bigger and bigger also in terms of the program. Next slide, please. So why are we organizing it? As you're well aware, there's a lot of interesting breakthroughs happening in the RL world, but the challenge is that they're happening in different areas. There's folks working on algorithms, there's folks working on applications. And so, it's hard to bring everybody together at the same table. And so next slide, please. The point of this workshop at this also specific event, as you know, BuildSys is also organized between different areas, CS and civil. And so our LAM, the goal is to bring together all those people focusing specifically on RL from different backgrounds and get different perspectives, and also move the field faster than if you were to, stay siloed in your specific areas. I don't know if you can say traditionally, but this year and also last year, we had a lot of presenters and contributors from the national labs, which is, I think, a very exciting thing, because it shows that this topic is moving from pure research to more applied in an area where contributions can be made and also directly applied in the real world. And you'll see that in the way the setup is, the challenge. I mean, the sessions are set up. One thing that we also wanted to do, which would be a lot nicer in person, but one of the sessions today is more of like a hands-on sort of like session. So if you wanted to get started, and since we can do it as opposed to a more traditional conference, we'll have like live demos or demos from environments that you could hopefully start relatively closely after the sessions end. And you can get started in the field if you have no experience before, or if you're just interested in getting into a different type of environment. That's something that was requested from the community during the year in our conversation. So hopefully it's something we can deliver. I'm looking forward to that. So with that, welcome everyone, and I'll pass it on to the TPC chairs for their welcome message. Enjoy the conference.
Thank you, Zoltan. So can you hear me?
We can hear you.
All right. So welcome everyone. This is the RM21 outline. So opening remark, which we are doing right now. And then afterward, we'll do keynote 1. And then there's a session 1, which is related to application of RM buildings and related challenges. And then keynote.
I don't know if this is new.
And then keynote 2. And then we'll do some community announcement in the field of RL in the built environment. And the session 2 is follow up, and that's the benchmarking RL, and then another break. And then session 3, which is a last session, is what Zoltan mentioned, getting started with the RL, like showing various like RL environment to test your algorithms, and then they will basically show how to use those for the beginners who are interested in start to RL for the building control. And couple notes, like all times in GMT, and sorry for our mistake before, but now I think it's everything cleared. So it's a GMT. So now it's 9 a.m. in Texas, I think 10 a.m. for Eastern. So that's the starting time. And each presenter for session 1 and 2, you guys will have a 10-minute to present and short questions afterward. But moreover, like after like 3 presentations, we'll have a longer discussion, like around 20 minutes or 15 minutes to discuss about the whole like section theme. And please use your Zoom chat regarding your comment and question. And of course, using microphone is also fine too. Luckily, we are all in a Zoom channel, so it is very possible. So our first keynote is Hidia Zandi, and she'll talk about scalable load management system using reinforcement learning. And then keynote 2 is from Andre Bernstein. Sorry if I'm like wrong on pronunciation, but he's from NREL, and he'll talk about the data-driven control of complex engineering systems. In the session 1, as I said, it's some challenges related to application RL in real-world buildings. Session 2 is related to benchmarking. And the session 3 is getting started with RL. And it is important to note that if you go to our website, you can click those links. It's a hyperlink, except for just one environment. You can go to their GitHub page to see the details of it. Jan, do you want to add something about the review process?
Yes, maybe we can go to the next slide.
Oh, next.
We should have some summary.
This one or next one?
Yeah, this one. Thank you.
Okay, great.
So, yeah, thank you, Jun. So, as Zoltan mentioned, we had several high-quality submissions from academia, industry, and national labs. Each of the paper has been assigned 3 reviewers from our technical committee, which was also a diverse combination of the industry, academia, and national lab representatives. The technical committee chair selected 6 papers with the highest scores that are implementing reinforcement learning in a range of modalities for buildings. And we invited 3 presentations for RL testing environments. So that's everything from the review process.
Okay. And I added one slide, like just basic counted, like where are you guys from and where are you guys from? So the presenters are from 6 universities, 5 national labs, and 1 company. So it seems very well mixed. I mean, if I group national lab and company as a one big chunk. So it's a full mix of university and national labs and 1 company. And then reviewers, I should say, I mean, the reviewers as well, because they're an expert in this RL in the built environment. So 8 universities, most likely professors and PhD students, and then 6 national labs and 3 companies. So we are well mixed in both presenters and reviewers. And from the country-wise, we have like all the like USA, and US is the most like the authors and presenters from, but also we have many people from Europe, like Denmark, England, France, and so on, and Canada, China, and also Singapore. So we hope to have more Asian and African continent or Australia, I mean, people in the future RLAM, but we're moving forward. All right, so I think we can do some group photo time. So if you are available, please turn your camera so that I can take a screenshot of our Zoom image. Okay, let me share my, oops. Done. Let's do it this way. And then I think we're all fit in a 1 page. That is good. All right. Cheese or whatever. Oops. I'm not sure. Let me do it again. All right. Let me do it again. I think Silvio just joined, so. All right, thank you so much. Let's go back to our slide. Okay, so that's almost all that we are going to like welcoming you guys. So it is time to start the keynote. I think we have a 5-minute earlier than our schedule, but it is good because we can have more time for Q&A. So it is my great pleasure to introduce Hilia Zandi, who is from Oak Ridge National Lab. And Hilia Zandi studied computer engineering at University of Florida, and she is currently a research and development staff in the Computational Systems Engineering Group in Computational Science and Engineering Division at Oak Ridge National Lab. Prior to joining ORNL as a modeling and simulation software engineer, she worked at ProNova Solutions as a researcher and software engineer in imaging and positioning team. She developed sophisticated automation methodologies for accurate robot positioning and robot calibration at the time. And now her research expertise includes machine learning, robots, advanced analytic, cyber-physical system, large-scale building to grid integration, and design and developing optimization and control platform with an application to buildings and energy systems. So Hilia, stage is yours, and please welcome Hilia from our hands.
Thank you, John, for the introduction. Let me share my screen.
Okay. Do I need to give a permission to you, or is it?
No, I think it should give it to me right now. Just let me know if you can see my screen in presentation mode.
I can see that.
Okay.
Yep.
So, hello everyone. Thanks for joining this presentation, both virtually and in person. So in this talk, I would like to give you an overview of various model for reinforcement learning that we have developed and field tested over the years to optimize the energy cost in for building loads. Before going into the algorithm development and showing you the result, I would like to set the stage first and talk a little bit about the problem that we are solving and what is the effect of emerging technology on the power grid right now. In the past decade, we all have noticed a lot of penetration of smart devices in the market. We are seeing more and more smart thermostat, smart water heaters, smart plugs, and it's really important to be able to monitor and coordinate the power that is being consumed by these devices. At the end of the day, most of these devices will be used in a building of some sort, and buildings are accounting for about 41% of the energy that is consumed in buildings. And this shows the significance of saving energy for buildings. And the good news is that we have the potential to save up to 40% of this energy through advanced sensing and control. So based on all these changes that the grid is seeing because of the evolution of the Internet of Things, more sophisticated loads that are being introduced to markets such as electrical vehicle charger, and more integration of renewable generation such as solar, what does the power grid really need? So it basically needs a reliable and secure load management system, which can be installed and basically deployed on grid infrastructure, and then can access the flexibility in loads and manipulate them based on some sort of intelligence and optimization. So that's why a lot of research has been done to developing various optimization methods. So the simplest one are the rule-based methods, which are simple, but they can be effective for various cases. However, they cannot deal whenever we have multi-objectives. The other one are model predictive control that have been well studied for building applications. They can handle the multiple objective. However, as the name suggests, they require a fully known model of the environment and equipment. So that's why they cannot really adapt well. So for each equipment and the building or any changes that happens, we need to create a new model for that. And reinforcement learning, which has mostly been used for robotics and gaming, in the last few years, it has gained a lot of attention for building application, and it potentially can address many challenges that we are seeing for model predictive control and the rule-based. So because of that, in this project that I'm going to presenting for you today, we decided to design, develop, and field evaluate a scalable load management system using reinforcement learning. This project is funded by DOE ERE Building Technology Office, and we have three main objectives in this project. The first one is to develop reinforcement learning optimization and control methods to basically understand the pattern of the energy usage in equipment and buildings and create the optimal load schedule. The second objective here is to develop a scalable load management system which can access the flexibility in loads and manipulate them based on the result of the optimization method. And the last objective is to perform field evaluation to basically both check the software, demonstrate the flexibility and the scalability of the software framework, and also demonstrate the benefit that one can gain by running model-free reinforcement learning optimization and control in buildings. So the first thing we did was to create a scalable load management system. Here we use a hierarchical cloud-based multi-agent system architecture in which we have a community of software components that can collaborate with each other to satisfy the overall system objective. All the software components that we have been developing is running on Amazon Web Services. We are using DynamoDB as a cloud-based database, which all the agents can query and save the information. Here we have three main components. The first one is the home agent, which works at the lowest level and basically handles everything that is related to homes in terms of monitoring the sensors, controlling the actuator and the devices, send us current state of the environment and save it to the DynamoDB, or reading the generated policy from the learning agent and then dispatch them to the environment. The second one is the learning agent, which basically queries the information from the DynamoDB, run the optimization and model for reinforcement learning, and then generates new policies so the home agent can basically read them and dispatch them in the environment. And the next one is the aggregator, which basically handles the coordination between the decision that makes by different buildings in its community. And also it handles as a broker, if you will, between the utility signal and the homes. One more thing that we developed was the graphical user interface container. And the goal for that is to basically let the researcher to basically have access to the field deployment result and how the building and the actuator is working based on the latest algorithm that was deployed in the field. So we can basically, using a username and password, log into the information, look at the latest information, see if there is anything wrong or if everything is performing as expected. We can query the results since the beginning of the field deployment, see if there are any alerts, etc. To test the scalability of the software, we use 7 virtual machines. The first virtual machine contains basically the aggregator agent and the GUI. We have the DynamoDB, which basically all the agents use to query and save the information. And then we wanted to test the scalability for a community of 50 homes. So basically for virtual machine number 2, 3, 4, we assigned 15 homes, and for the last one, we gave it a little bit more homes. And then we run home agent for 15 homes and learning agent for 15 homes. So basically, the home agent will sense the environment, send the information back to the DynamoDB. The learning agent periodically will check the state of the environment, run the reinforcement learning algorithm, and generates new policy and rules and send it to DynamoDB, and the home agent can read them. And then for each of those virtual machines, we create another virtual machine which have the simulated API and building and equipment simulator. So the goal for that is basically to be able to test both the software and algorithm as they will be deployed in the field. So basically in the simulated API, we are mimicking the same behavior you can see whenever you are dealing with vendor application. We have programmed the delays you can face, the bad information from the server errors, if there are bad data, how the software will manage them. On the other hand, for the building and equipment simulator, we integrated the model of the building or the environment or the equipment, if you will. So whenever the home agent wants to check the send the dispatch command, the thermal behavior of the building or the equipment will change accordingly. And the next state that it's going to receive based on the result of the reinforcement learning algorithm decision, it's going to match accordingly. So we run this test bed for about 2 months. And everything was running smoothly on the CPU and the RAM usage. Everything was within the acceptable bandwidth, which was a good thing for us. And I mean, that was the goal of the software development. So now let's talk about the control development approach. So the first thing we did was to develop the model. We wanted to start simple. So we started with single zone, single family house with single stage HVAC system. And then go make it more complicated. We go to 2-zone single family house with 2-zone HVAC system. And also we had a hybrid water heater, which both have elements and heat pumps. So all the data here that we are using for model development is collected from a research house that we call it Yarner Station Research House. It's owned by ORNL. It's basically, you can see the picture here. So it's a real 2-story residential house in a Knoxville residential neighborhood. It's highly instrumented, so we have access to metering data, temperature data, pressure data, humidity data, and then we collect the data from the Yarner Station Research House, develop our models, test them, and after the accuracy is acceptable, we go and integrate it with the simulation testbed. And this simulation testbed is basically serves at the beginning as an environment for our algorithm development I wanted to emphasize that this model development has nothing to do with the algorithm development itself. It solely is there because creating a simulation testbed, and we wanted to start with simulation testing first and then go to field deployment. So we created single zone building, single stage HVAC system simulation testbed, 2-zone building, 2-zone HVAC system simulation testbed, and water heater simulation testbed. Then we started on working on the algorithm development. So there are 2 types of model-free reinforcement learning we are working on mainly in this project that I'm going to talk about. So deep Q network and deep deterministic policy gradient. So before talking about the algorithm that we have designed, I want to talk about the reinforcement learning a little bit. I know most people that are attending this conference, most probably have some background in reinforcement learning. So I'm gonna make it short and high level. So reinforcement learning is a type of machine learning that optimizes the decision-making strategy of an agent in an unknown environment. There are basically two types of reinforcement learning, model-free and model-based. In the model-based, as the name suggests, the agent requires a fully known environment, a model of the environment that is dealing with. So the accuracy of the optimization is perfect or almost perfect. However, as you can imagine, it cannot really adapt to the changes in the environment. On the other hand, for the model-free, we don't need a model of the environment. So basically, the agent simply learns about the environment by interacting with it. So it senses the state of the environment, make a decision based on the feedback that is received from the environment in terms of penalty or reward. It adjusts the policy or how it's a strategy to taking an action. So in this project, our focus is model-free reinforcement learning, which again has two types, value-based and policy-based. In the value-based, the agent basically estimates a Q value of a state action pair and most of the time uses the chooses the action with the highest Q value. For the policy-based, we generate the probability of all feasible action for the current state and choose the one with the highest probability. So I'm going to talk a little bit about the two algorithms that I said we are working on here. The first one is deep Q network, which is a combination of Q learning and deep neural network. So here we have two deep neural network, evaluation network and target network. So the input to the network is the current state of the environment and the output is the Q value. Both the evaluation network and target network are initialized with the same structure and same weight. And after every delta T update of the evaluation network, we make a copy and copy it to the target network. So basically the role of the target network is as the ground truth that we have in supervised learning. So it basically guides the evolution of the algorithm. And whenever the mean square error between the evaluation network Q value and the target network is small, then we know we have converged. The other one is deep deterministic policy gradient, which is a policy-based reinforcement learning algorithm and is designed for solving a control problems with continuous variable. And here, if you want to the action to be a single set point, so that's counted as a continuous action space. So here we have two network, actor network and critic. So the input to the actor network is the current state and the output is a deterministic action. And the input to the critic network is the current state of the environment with the action that was taken by the actor network, and the output is a Q value. So basically, in simple terms, the role of the actor is to make a decision. The critic says how good that decision was. And again, each of the actor and critic network has two evaluation network and target network. So we are dealing with four deep neural network here. Okay, now we're gonna go through some of the algorithm development process that we did. So as I mentioned, we first collect the historical data from Yarn Station Research House, create the model, integrate it in a simulation testbed, and then the reinforcement learning algorithm will utilize that simulation testbed to learn. And actually, we will continuously modify the algorithm based on the result until we are satisfied with the result. And then the next stage is virtual deployment. The goal for that virtual deployment is basically to mimic everything that we're gonna deal with when we go to the actual deployment. And the reason we have that, we really didn't want to deal with debugging the software or the algorithm when we are deploying it in the field. So as I mentioned before, here in the virtual deployment, we have the API simulated, we have the billing and the load simulated, and everything can be tested as it would be deployed in the field. And after we are happy about the result, we go to the deployment stage, which the RL agent will basically deal with real vendor API, deal with real sensor, real actuator, and they just do the learning and everything based on the real data. So because of the time, I'm not gonna talk about all the results we have. So I'm gonna start with the HBA system optimization for two-zone single family building, which we collect the data and create a simulation testbed based on Yarn Station data. So here's a sample of what we, how we define the state, action, and reward function for DQN. So here the state is the time of day, the indoor temperature at that time, the outdoor temperature at that time, and the price signal with the forecasted price signal. The action space, so the result I'm showing is for whenever we have the action space set as the on and off status of each of the AC for zone 1 and zone 2. So the combination will give us 4 different actions. A0 corresponds to the case that HVAC system for both zone 1 and zone 2 is off. A3 corresponds to the case that HVAC system for zone 1 and zone 2, both of them are on. And A1 and A2 correspond to the case that the HVAC system for one of them is on, for the other one is off. And here we define the reward function as negative of the energy cost and the discomfort. So basically our objective here is to minimize the energy cost and also the discomfort. So let's look at the validation data. So the diagram on the left side shows the result of the baseline, and the diagram on the right side shows the result of the R algorithm. So here we define the baseline as the point, as the case that we have a fixed cool set point for the RL, that it's just gonna keep the room temperature at the set point without having any advanced control. So we put